Hello, my name is Francisco. Me and my colleague Alexandre will present a paper named RFID Technology for IoT-Based Personal Healthcare in Smart Spaces. The motivation of the paper goes through a possible boost on the current evolution of the traditional medical model that can be provided combining IoT and the RFID technology. The emerging paradigm of IoT and the wide variety of increasingly cheap sensors have the potential to put in place personal smart health systems. These sensors have some desirable characteristics such as low cost, energy autonomous, and disposability, which suggests a possible availability for hosting new interconnections between the environment of the person, his body, and the internet, at the purpose to produce and manage participatory medical knowledge. They also gather information about the user's environment and can collect and process data about the human behavior. The progressive aging in population demands modifications on how to give care to older people in order to ensure a decent quality of life. IoT and a wide variety of cheap sensors have the potential to put in place personal smart health systems that can monitor the behavior of the person, as well to compile statistics, activate alarms, or prompt for remote actions. One of the variety of potential technologies that can be used is RFID, radio frequency identification. A passive RFID system is composed of the tag, which is a digital device, an antenna, an IC chip with unique ID, and a radio scanner device called reader. RFID is mostly used in logistics. However, and aligning with the aim of the paper, RFID systems can also be used for personal healthcare from an IoT perspective. The survey done described in the paper covers passive devices which are capable to provide services and enough width ranges to implement a network of sensors for tracking human wellness and monitoring the quality of the local environment. With reference to figures A and B, a RFID-powered environment could be a smart house equipped with a distributed network of readers, enforcing a coverage in the most relevant spaces of the house. Readers may interact through Wi-Fi or Bluetooth links. Finally, data gathered, for example, interactions of the user in the house, can be processed by data mining algorithms. Furthermore, the whole technology must be compliant with the electromagnetic safety standard concerning the power absorption in the human body. There are several types of sensors, and now I'll introduce the environmental passive ones. These sensors can be distinguished between volatile compound sensors and temperature tags. Critical parameters for clinical diagnosis, like temperature, humidity, and gases, can be monitored by this type of sensors. Regarding the volatile compound sensors, these have a properly shaped antenna that hosts CIMs, chemically interactive materials. This means that this tag detects a wide variety of gases, obtaining information about the presence and concentrations of these in each area. Several kinds of chemically interactive materials can also be combined into a wireless nose shown in figure B. This feature is basically a 3-for-2 matrix of tags capable to respond in a selective way to the presence of different vapors such as water, ethanol, and ammonia. Concerning the temperature tags, this can be divided into 3 classes: threshold temperature sensors, continuous temperature sensors, and digital data loggers. The first one, the threshold temperature sensors, are sensors that exceeded a given threshold, such as a value of temperature or humidity. The material changes its state. and the event is written into a physical memory. These devices could have application to the assessment of food and drugs integrity, as well to the detection of fire. The continuous tempered sensors are an RFID sensor that involves a chemically interactive material capable to continuously react to the change of temperature. An example of the use of these sensors can be in water regions close to the tag, whose conductivity and permittivity change with the temperature of the water, and accordingly modify the tag's resonant frequency detectable by the reader. Digital data loggers are the autonomous feed temperature sensors that are equipped with an integrated temperature sensor and with a local analog to digital converter. The temperature informations are read from the tag straight away into a digital form. These are expensive and have poor power sensitivity than conventional feed chips, due to the both passive and battery-assisted mode that these chips can be used. Now, the body-centric feed tags. These tags are autonomous feed tags that are suited to be put in contact with the body or in its close proximity. They are fully transparent to the user. These tags are split between wearable feed tags and implantable feed tags. Regarding the wearable feed tags, these are tags that are put in people's clothes. Although high electromagnetic loss is provoked by the human body, the antenna-body electromagnetic interaction can be minimized by using multi-layer tags, such as dipolus with dielectric insulators. Nowadays, the maximum read distance achievable with an RFID transmitter may reach between 5 and 6 meters. Current link performances are already enough to track a person provided with two tags placed over the front and rear torso inside a regular wound, shown at figure B. Now, the implantable feed tags are tags that have a technology that has been demonstrated to be potentially useful to take care of the human health states from the inside by labeling, for example, body prosthesis or orthopedic fixing. Each item could be monitored in real time or on demand by the IoT infrastructure for the ambitious goal of monitoring biophysical process in evolution, such as tissue regrowth. The major challenge in the design of implantable tags is to establish a convenient communication link by using a reader power that is compliant with local emission regulation. The figure shows the minimum power that is requested to the feed reader to turn on a small dipole tag implanted in different positions into an homogeneous phantom resembling the human body. In the graphs, the 30 dBm straight line indicates the maximum available power for typical commercial readers. The diagrams show that establishing a feed link with subcutaneous implants up to half a meter from the reader, up to 1 meter in the near future, is nowadays a feasible target with promising applications to the monitoring of some particular body areas and vascular prostheses. Now, my colleague Alexandre will continue the video introducing data processing and human behavior analysis.
So, now we're going to talk about data processing and human behavior analysis. By processing everyday data, we can find specific patterns of actions of a person. In this figure, we can see an experiment of a person walking from one side to another and then back. We can also see that the tags react accordingly when the person passes in front of them. For example, in tag 1, we can see a spike downwards when the person passed in front of them, and we can see that in all the tags. With this sensor, we can get information about human activity. For example, we can know where people are in the building, and it can also be useful to identify some problems. For example, cardiovascular pathologies that produce a progressive slowing of the walking capabilities. And it might even be able to see if someone has passed out or fell. Uh, in the case that a person is walking, for example, from tag 1 to tag 5, but never passed from tag 3, just stopped there and didn't go back, so we can assume that he fell. About gesture recognition. The wearable tags can be used to detect motion. This way, it can sense if a limb is moving, and therefore if it's compulsory or not, which might give us more information about sleep disorders. It can also give us more information about the state of the user, if he's standing or moving, and it might be possible to check if he's laying down or even sitting. In this figure, we can see how the tag reacts to 8 different movements. And we can also notice that each movement creates a different reaction, so we are able to identify what the user is doing. About remote monitoring and control of the overnight living environment, we can combine both tags so that it can help monitoring children, disabled, and the elderly in hospitals or even at home. This is able to detect if someone needs immediate attention. In this picture, we can see a prototype that has been created. And this prototype has a reader antenna, wearable tags, and environmental tags. The information that's processed by the sensors is passed to a web-based graphical processor, where it shows all the information about the user. We can also see the reactions of the tags and information about when the user moves. For example, when the user moves, we can see spikes in the body tags. When when he's not in bed, we can see there's no spikes, there's no activity. We can also see that when he moves in the carpet, there are also spikes. We can also know useful information, for example, if he fell, if he's absent from the bed, if he's still moving, or if he is still sleeping. About safety compliance issues, there's the question of radiation. While RFID can only be used within a room under the constraint that the electric field emitted into the environment, the radiation can affect the human body, and it could be harmful to the person. While in this picture we can see that from a certain distance, the radiation first of all, the radiation does not reach the user in A. And in B, we can see that after a certain distance, 1 meter, the SAR or the specific absorption rate is very low. And even after 3 meters, it's less than 1. So meaning that the user is not in any immediate danger because of radiation. About challenges and future research. First of all, we have a problem of stability, accuracy, and reproducibility of environmental sensors. Because chemical sensors aren't still mastered, we need to get more accuracy detecting certain gases. We need more research to know what gases react to what chemicals. We also don't know how the sensors will react in a real environment with all the dust and the dirt. About autonomous RFID nodes and data processing, there are still problems with the cost of the infrastructure. Since there is too much data to analyze, it can be very expensive to pay for the computational power. Ideally, we could get an handheld device to show the information, but this would be way more expensive. With the RFID synergy with epidermal electronics. So, what are epidermal electronics? Epidermal electronics are something are a degradable type of ink that you put on your skin with electronics. And if you could combine the RFID with these electronics, we wouldn't have the need of having several clothes for the wearable tags, meaning we could cut on the wearable tags. Uh, Knowing this, the skin might become a problem to the electromagnetism communication. So there's still a lot of questions. Electromagnetic social interactions, it's about, with machine learning, learn about the interaction between people. Uh, for example, in the classroom between different children, or in the nursing home with elderly. To conclude, this technology is still in early stages. Um, there are some institutions researching this technology. However, there are not that many manufacturers. So for us to advance with this technology, we'd have to reach an agreement with them. Um, However, it could be still very not advantageous to us because it's expensive. But if we could advance this technology, it could become very beneficial for people in elderly homes, children, and just sick people it could be way easier to help. And that's it. Thank you.